Okay. What else on the homework? Yes.
Number 51.
51. Okay. Anything else before number 51? Trying to think if there was something else that we had in the other class that came up. Nope. Oh, I know what we wanted to do. Before 51, I would like to go through 29 through 34. 29 through 34. Now, just to quickly review. Yesterday we talked about over and under approximations. Okay? Now, a left sum is going to be over when? Decreasing. Because if it's decreasing, a left rectangle is going to be over. If it's increasing, a left rectangle is going to be under. Okay? A right will be opposite that. Okay? So increasing and decreasing, what's the matter? What about a trapezoid? Concave up. Because if you've got a graph that's concave up, a trapezoid is going to be an over approximation. Okay? Concave down would be an under. And then what did we say about midpoint? Opposite. And that was because of what reason? The pivoting thing, right? So if you've got a midpoint here and you've got this curve, if you've got this curve that misses the whole thing, if we pivot that edge, yeah, we would get a trapezoid that would be under. Okay, it would be tangent, it'd be under. So it's opposite. Okay, so 29. So 29 says if you have a positive and increasing function. So if we have a function that's positive, which means above the x-axis, and increasing, it could look like that, it could look like that. We don't know. Okay, but it's increasing. And I is the exact answer. Is a left going to be less than the exact answer? In other words, will the left be under? Yes, because it's increasing all the time. Must be true. 30. Would a midpoint be less than? Depends on the concavity. If it's concave up, a midpoint will be under. If it's concave down, a midpoint will be over. So it depends. It may be true. 31. Is a left less than a right? Left is under, right is over. Absolutely. Must be true. Is a left less than a midpoint? Is a left less than a midpoint? 32. Must be true. 33. Is a left less than a trapezoid? Must be true. Now I think if you looked in the back of the book, you would have got it wrong because they are wrong in the back of the book. Number 33, I think, according to what the other class said. Now, I don't know if you looked or not, but now let's talk about it. Go back to 32. Why does a left have to be less than a midpoint? Alex.
Because the midpoint's more accurate and the left isn't under approximation.
Left is definitely under. We just got in saying that midpoint we don't know. Midpoint could be under or over. Well, if a midpoint's over, then clearly a left will be less, right? Because it's under. But if a midpoint is under and the left is under, the left is more under. That's the key. Now, I want to talk about this just a quick, for a minute here. A left, when is a left a perfect fit? If the graph is horizontal. Well, that hardly ever happens. Most graphs are not horizontal, and so therefore a left is going to have a fair amount of error. When is a trapezoid, same with the right, when is a trapezoid or a midpoint a perfect fit? Anytime it's linear. But it can go up or down, so that would take into account a lot more functions. They do increase, or not, most of them aren't linear, but they do go up and down. So trapezoid and midpoints are going to be better approximations. You're going to have less error than lefts and rights. Simpson, turns out, is a perfect fit for parabolas. If you did a Simpson's rule and did S4 on a parabola, or S8 or S anything on a parabola, you get the exact answer. It has no error. So that's why Simpson is even more accurate than trapezoids and midpoints. Because any curve is going to vary from a linear situation, but it's not going to vary as much from a parabola curve as it will from a linear situation. So the closer a curve is to a parabola, the closer Simpson's will be. One of the reasons that Simpson is a better approximation, but it's just one more step in the line. And we're not going to get into why it fits a parabola, but that's another little interesting thing about these deals here. Okay, 34. Is a trapezoid less than a midpoint? So the answer would be might be true, right? Might be true depending on the concavity, okay? But we don't know. We don't know. If it's concave up, midpoint would be under. If it's concave down, midpoint would be over. So we go there. All right. So you'll have some more of those on your homework, and there'll probably be some of that on our next quiz as well. Okay, now let's talk about 51. 51 talked about this divide and conquer strategy. I just want you to there's a couple things I want you to understand about these errors. But if I had a function that went like this, and let's say this is 1 and this is 3 and this peak, we'll just make it easy. Let's say it's right there at 2. Okay? And first let's talk about left and rights, and then we'll get to number 51. If I was going to do the integral from 1 to 3, and I didn't know what that exact area was, okay, I could divide that up, that's the divide and conquer part, into the integral from 1 to 2 and the integral from 2 to 3. Now why would I divide those up there? Well, I would find this max point because what do I know about lefts here? They're under. So I could do 10 lefts on this part from 1 to 2. And then I could come over here on the part from 2 to 3 and I could do 10 rights. And what do I know about 10 rights over here? Also under. And I could add those up and I would get some number, I don't know, let's call it A. Okay, I'd get something, but I would know A is under the exact area. Okay, then I can come back here and from 1 to 2 I could do 10 rights. And I would know those are over. And I could do 10 lefts here from 2 to 3. And those would be over. And I could add those up and I'll call that number B. And I would now know that my exact area is trapped somewhere between A and B. Because I did a known under approximation, and what I did was I divided it up because if I was using left and rights divide on increasing and decreasing. So I divided the curve up into places where it was only increasing and places where it was only decreasing. The word they use in the book, by the way, is monotonic. Monotonic means always increasing or always decreasing. Mono means one. Tonic means change. There's only one change. There's only one direction. Monotonic. Okay? All right. So that's what they're talking about, divide and conquer. So in 51, and I want you to get this on your calculator screens right now, if you would. So go onto your calculator and go into the calculator screen. Okay? Go, and I think I had you do this yesterday, but the function is sine of x squared. Maybe I did. Okay, Alex, you go on. I want you to do it. I want everybody to do it. So go to your calculator. No, go to your calculator screen first. I'm sorry. How many times do I have to say calculator screen when I really mean graph screen? Go to your graph screen. Go to your graph screen. And for f1 of x, let's put sine of x squared. Sorry. Sine of x squared. And now, didn't we do something with Zoom Fit yesterday?
No.
Zoom Fit doesn't sound familiar? Okay. All right. So what I want you to do is go to your window. I want you to go to your window. This is good because we'll be doing a lot more with the calculators the rest of the way here. And so go to your window settings. And let's set our x min and max to 0 for the x min and 2 for the x max. Because anytime we have an integral, we have a left and a right edge, right? We have the definite integral from a to b, and so we'll be able to set those. And once we set our left and right edge, our x min and x max, go ahead and hit OK, or hit enter. Once you've set your left and right edge, now go back to your menu and go to, why is that, there we go. Go to your menu and go to Zoom Fit. Go to Zoom Fit. And what that does is it takes your graph and it says, okay, you want to look from 0 to 2. I'm going to figure out all the y values between 0 and 2, and then I'm going to set your window so it'll fit. That's what it does. So it's pretty cool. So if you know your set domain, Zoom Fit's a great thing to do. All right. So now we want, on 51, they want us to divide and conquer based on the midpoints and trapezoids. Well, when are midpoints and trapezoids under and over approximations? When the concavity changes. So we're going to want to find what? Flex points. Now, you weren't required for this problem to actually do it, but I'm just going to show you where the calculator can do this pretty quick for us. Go to Menu and go to Analyze Graph and go down to Inflection Point, number 5. And it's going to ask you about where do you want to look. So lower bound, get a little bit left of where you think your inflection point is. Get right in here somewhere. Get right in here somewhere. Okay, and then get past it a little bit for hit enter, and then get past it a little bit. Okay, notice as soon as you get past it, and then go ahead and hit enter. And then grab that and kind of move it out of the way over there. You can grab that text. There you go. Grab that and drag it. Yeah, there you go. Now slide it. There you go. Okay, 0.808. So we have an inflection point about 0.808. Now we have another one probably somewhere else. So what that means is that we could take this integral and we could divide it from, what was it, 0 to 2? So we can divide this integral from 0 to 0.808. And then, again, you don't have to worry about writing all this out. But the idea is that in that area it was concave up. So what would be under? What would be under concave up? Midpoint. So we could do, say, 10 midpoints there. And then from 0.808 to whatever our next inflection point was, we could do trapezoids. We could do 10 trapezoids, and those would be under. And then from whatever to 2, if there was another, and we could divide it up, and we could find a number that we know would be under the actual answer. And then we could do the opposite ones and find a number we know is above. And we know our answer is in between there. Again, what's the big deal, right? I mean, if we don't know how to do the antiderivative, can't we just type in our calculator and let it do it, right? Well, what we're trying to do here in Chapter 6 is analyze how's the calculator doing these approximations, dig in a little deeper with how it knows why it's off and how close it is. And it has to do with stuff we've learned with the chart. It has to do with increasing, decreasing, it has to do with concave up, concave down. That's why we're studying, okay? We want to get in there and we want to understand a little bit about these approximations and what the calculator is doing and how it's doing. All right, so that's what 51 was about. Okay, what I want to do at this point, I think, is I'm going to send you this file that we're going to get to use. So I've got 13 people logged in. Okay, who's not logged in? Why not? What's that? Oh. Okay. Who else? Why not? Is it in there? It is in there? Oh, it was in there the other day, wasn't it? It wasn't?
Not funny.
I thought it was in there the other day.
One that looks like it.
Okay. Do you have it with you?
Yeah.
Okay, why don't you put the hat on it and put it in the thing, and I think it may still send.
That's 2 people.
Yeah.
Where's the third? Yeah. I said.
Zach's gone.
Now there's 4.
What? Why did
Somebody-
you just lock me out?
Again?
Well, try logging back in.
You want the
How do you go now?
Try. You got
Yeah, just
Scratch
erase that earlier. Trying to dial.
Let's see.
No.
Oh.
Oh.
Try saying because it's not. Can I have a glue with this? I mean, it's just tell me all that new
Oh,
list.
yeah.
There's like a little rock under my hand.
That's what it feels.
Oh.
Stays, dude.
I know.
My scar.
That's right. It's one of your
Absolutely ones.
The door hit me like
That other
this.
resident says.
Yeah, it's like a
Yeah.
scar up here and a scar down here. I've been.
Smuggling food. I'm gonna take them all.
Tiger.
Yes.
Shut up. In the car. And the door could be
All right. Well, hopefully you will remember to get your calculators charged before the next quiz, or yeah, it will be really difficult. All right. So I'm going to go ahead and send this. Now, I've got to do something a little bit different here. I haven't quite figured out the specifics of this, but I'm going to send it to a folder that's called MyLib for library. You think so? Did anybody get it?
I haven't gotten
I just
Try it.
That was the old one we got.
it. You sent it to Alex.
Okay. I just sent it
There we
down.
go.
All
I got it.
files. Oh, all
Okay, I
files.
sent it to Alex, and then I sent it to Alex again. Okay. All right, so everybody got it. So this is called the area. So go to your
That's it.
go to on, go to my go to your home screen, go to My Documents, and go into the MyLib folder. That's your library. Now, and then go ahead and open that up. The area program that I just sent you. Okay, and okay, and you should have this on your screen right here. Okay. All right. Now, all right. Who did we get? Danny.
Oh, it is.
Okay. So now, the main screen here, it says, put this in the MyLib folder, press doc save as. We shouldn't have to do that because we put it in there. We do want to refresh the library, so go to the doc button, under the home, right here, on here. Okay, should we get a new presenter? Go to the dock button down to number 6 where it says refresh libraries, and I think what that does is it lets the calculator know, okay, hey, there's something new in the library folder. But I haven't quite figured out with the programs on our old calculator. I knew how to write programs for that and do various things with it, and so I would kind of adjust them to make sure they kind of fit with what we wanted. But I haven't done that. I haven't figured out how to do it, and I haven't really spent much time with these to do that. But what I've read about it is if it's in the library, then these programs that we're going to use here, we should have access to from other documents, like from the Scratchpad and so forth. But I haven't gotten that to work. So anyway, we'll go ahead and we'll do it, but I'm not sure what good that did. So here's how this is normally going to work. If you have a problem, like for example, in a minute here, we're going to do a problem where we're going to do an L100 and an R100. Anything that's 10 or more, this is where this is going to come into play. Anything that's 10 or more in your homework on the quiz is automatically saying to you, it's okay to use this area program to get the answer and just write down the answer. That's all you have to do. If it's under 10, if it's like on the homework today, if it says a T8, that automatically means you write out, like we did earlier for that S4, you write it out, And then you can go to your calculator to add it up and so forth. Okay, that's the difference. 10 or more, under 10. All right, so we're going to go ahead and go to the next page. So hit Control right arrow to get to the next page. Control right arrow will get you to the next page. Okay, now, don't press enter yet. I know it says press enter. You didn't do it. Well, okay. Daniel did, thank you. If you did, it's not a big deal. But listen, all this is right here, all 1.2 is a calculator page. Now, but we're in a document, we're not on the scratch pad. See, go ahead and hit the scratch pad button over here, under the escape. See, that's our scratch pad. You can go over here to the hit the scratch pad again. See, that's a calculator page. That's in the scratch pad. That's different than being in the document, okay? So go ahead and close that scratch pad, and now we're back. We're in this document. Now, this RAM stands for Riemann Approximation Method. Okay, Riemann Approximation Method. Now, if we read farther, it talks about how it will find out. This little program will find left, right, midpoint, Simpson, and the exact area. It leaves out trapezoid. I don't know why they decided to leave out trapezoid. I know it's not a Riemann, so that might be why. But Simpson's isn't a Riemann either, and they put that in there. So we're going to have to do something separate to get our trapezoid approximations. But if you turn to page 376, turn to page 376, and we're going to do the sine of x squared integral from 0 to 1. Now, we just got done doing it from 0 to 2, but we're going to do it from 0 to 1. Now, here's what I like about this program. So if you get into the area program and you get on this 1.2 page, you can just type RAM. Go ahead and delete that all out of there, Daniel, just for the heck of it. Okay, it's something you can just type in. So if you type RAM right now, now watch how it goes bold. Once you get RAM and it goes bold, what that means is it recognizes that as a special function, a special program that's been saved. Okay, so type RAM and then the parentheses, hit a left parenthesis. Now go ahead and hit enter. Some of you have already. It comes up and it says you'll get left, right, midpoint, blah, blah, blah. Okay, press enter. Now you type in your function. So go ahead and delete that out of there. And we're going to type sine of x squared. Sine of x squared. Okay? That'll work. Okay? So you type sine of x squared. Then it asks for the left band. We're going to do 0 to 1. So put in 0. And then put in 1. And we're going to do 100 subintervals. So thanks for just a second or two. And there it all is. So there's L100. And if we look on page 376, they have all those written out there. Okay, there's R100, there's our midpoint, there's our Simpson, there's our exact. Now, just a quick little look here at the accuracy of these. Look at your left and rights. 100 of them. Still only is accurate to the first decimal place, maybe with rounding to the second decimal place. Okay? Midpoint is accurate out to about the 5th decimal place. And Simpson is accurate out to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. And with rounding, even the 10th decimal place. Okay? Yes?
Okay, for some reason when I go past the function screen, it says an error missing parentheses.
I'd say
We missed
Okay.
it.
Well, I would say somehow you might have deleted, hit escape. Okay, now that's interesting because when you typed in RAM,
No, I didn't.
It- okay, try it again. Okay, try and hit enter. Okay. Okay, that right there. Did you see that? You didn't.
Oh, you have to
You
put
didn't
the
type
right
sine of
one.
x squared. Yeah, you've got to put the right parentheses. All right. So, but there you go. So if they had asked for an S100 or an L100 or an R100, we would just run this little program and we would write it down. Now, probably they're gonna ask you something else besides that, but anytime we have 10 or more, we can use this little program. All right, but what about a trapezoid? What if we wanted T100? So go ahead and hit OK. And now you can, just like you can on your calculator page, you can arrow up if you want to and highlight that and hit delete and it'll go away, okay? And so this is just a calculator page. Just remember RAM in parentheses is how you do that program. Okay, now, there is a program called track. Good guess. Notice how it turned bold. Now, if he hits enter right now, he gets too few arguments. Okay, now, and the other programs that are in this area document do not work like the RAM one did, where it comes up and gives us an entry screen and we can just enter our stuff. I really like that, where you can just enter the things in, but we got a little more work to do for these other ones. So go ahead and hit OK, and we're going to control right arrow to the next page. Okay, and this talks about some different functions here. Go ahead and control right arrow again, and one more time. Okay, now on 1.5, it talks about some different approximation files that are on here. So go ahead and scroll down the page. And these are some programs that are in here. Okay, keep going. Okay, now, here we got, if you want to do a left only, you can type RSL, Riemann sum left. RSM for midpoint, RSR for right, SR for Simpson's rule. The one we probably care about is trap. And then there's one for a Riemann sum between two curves, but we probably won't get into that. But now, what you have to do, this is important, you have to have already defined your function in f1 of x. Not on the scratch pad. You have to have defined it in this document. And then what you type in, when you type your trap, is you have to type these arguments. These are called the arguments of the function. Now, why they do B and then A, I have no idea, but that's the way it's written, and I haven't figured out how to change it. And then the number of subdivisions. So go ahead and arrow back. Go ahead and go back to that page 1.2. Okay, let's first define. So type out define, and we have to do it in F1, not F of X. It has to be in F1. So let's define F1. No. The one goes after the F. There you go. Define F1 of X equals sine of X squared. Hit enter. Okay. And now you can type trap, and then what would we type in the parentheses? Because we're going 0 to 1, right? So we type 1 comma 0 because it's B comma A comma 100. And this would give us 100 trapezoid approximation. So we have 0.31028, I think is what they say in the book. Okay? So for trapezoid, you'll have to do that. Now, again, you have to be inside of this document. If you go, Daniel, go to the scratch pad again. Go to the scratch pad again, and this is a part I haven't quite understood. If you type trap right now, okay, notice it doesn't go bold. So nothing's gonna, it's not gonna work. If you type RAM, it doesn't go bold. And see, that's what I think should happen when it's in the RAM, or when it's in the library. I think you should have access to it when you refresh those libraries. So I'm not quite sure why that's not working. Okay? Definitely gonna have to get a new presenter. All right. So that's one part of your homework. Is there'll be some questions where you get to just use the program, okay, and do that. So 10 or more, use the program. All right. Under 10, we write it out. All right. There's another. One last thing to go over here, and then I'm going to give you work time. Okay? All right. Oops. And so this would be something to put in your notes probably. And this is they're going to talk about an error bound. Okay, an error bound. Now, to me, that's very similar as talking about max error. Now, they're not exactly the same thing, but they're very similar. Okay? We'll use them almost synonymously. Now, the way that's usually going to be written is using an absolute value. Okay, let me change that n to say a 10. Okay, write that down there. Now, yesterday we wrote down the thing with the absolute value. We wrote down the left side, right? What does this mean on the left side? Amount of error. That's the amount of error that 10 left rectangles have. But then we've added in here this less than or equal to. So what's this mean? This is saying that the amount of error is less than or equal to 0.05. Well, what's that make the 0.05? The max error. Because what it's saying is that the amount of error is less than or equal to 0.05. It's got to be, that's the most it could be. That's the most it could be off. So that's the max error. This is an error bound. Okay? Now, if we remember from algebra, we could take the bars off of there and we could put 0.05 on this side and negative 0.05 on this side. Right? That's one of the things you did with absolute value equations. We can add L10 to both sides. So another way of thinking about this would be that the exact area would be somewhere between the L10 approximation plus 0.05 and the L10 approximation minus 0.05, right? The actual area has to be somewhere between there. That's more of a bound. It feels like more of a bound when it's written this way. This would be lower bound, upper bound, okay? But when it's written this way, we think of it as they call that an error bound. That's the most it would be. Now, one of the things you have to understand as we go through the next 3 or 4 days is that max error, there are good max errors and there are not so good max errors, okay, or error bounds. For example, let me give you this example. I shouldn't say good or bad, I should say useful. More useful and less useful error bounds. If I said to you that the amount of money in my pocket right now is less than or equal to $10 million, that would be a bound. That would be a bound on how much money I have in my pocket. How useful is that in telling you how much money is in my pocket? Not very useful. It's a true statement. The amount of money in my pocket is less than or equal to $10 million is a true statement. Also a true statement is the amount of money in my pocket is less than or equal to $30. That's also a true statement. Gives you a lot more insight into how much money I have in my pocket than the $10 million. Okay? So if I was to do an approximation and say this, right? That's not very useful. That the amount of error is less than or equal to 10,000. Right? That would tell me that the error is somewhere between 10,030 and 10,060. Or excuse me, 10,030 and negative 10,030 or something like that. Well, that's not very useful. Okay? So the smaller this is, but still be a true statement, the more useful it is. Okay? So that's one of the things that we will be talking about and you'll be getting into with your homework. Now, I'm guessing you'll have some questions about that as you get into it, so I'm going to let you get into the homework, and then I will answer those as you come up with those questions. So, there's going to be some homework questions that are similar to yesterday, some where you have to write stuff out, some where you have to do the over-under thing. You have to say might be true, must be true, can't be true. And then there's also gonna be some of these new ones that talk about airbound a little bit, and there's gonna be some that talk about, where you use your calculator, the area program. So we're gonna do the second line here on the homework sheet. Second line on the homework sheet, and you can use the rest of the time to do it. As you come up with questions on some of those, which I think you will, I can discuss that with you. Also, if you use this old solutions manual, the blue solutions manual only went up through chapter 5. So, it says volume 1, this one says volume 2, so if you're ever